of the notion of alpha being useful. That's lecture 3. So that's this one here. So a little bit about classical test theory and how reliability is indicated within this framework outside of measurement models. So this is a lot of foreshadowing of things that will show up within latent trait measurement models and how it used to be done back in the day before we had maximum likelihood. So here we go then. So big picture, what's this class about? Latent traits. So I've tried to list all of the synonyms for trait that I can think of. Across the models in this class, the latent trait to be measured is called a true score, a factor score, theta, latent construct, latent variable, latent factor, latent trait. Can you think of any that I missed? Yeah. Little Jiffy? Yeah. Yes, there's an article I gave you on, with about how to do EFA, and they're like, okay, if you must, here's how to do it. It's okay. But yes, um, the key thing here is that all of these indicators, all of these traits are things that we need observed indicators for. It's nothing we can measure directly. I heard someone say the other day, it's not like we can take a blood draw and find out what your level of depression is, right? There's a lot of processes that you can measure exactly, and there's a lot of things that you can't. And so these models are designed for the latter, things that you can't. There's 2 ways that we use the observed variables thought to measure these latent traits. We can either add them up and call that the trait, or we can fit measurement models in which the trait is thought to be a latent predictor. So this will be the last lecture focusing on the former, and then we'll get to the latter next week or the week. Yeah, next week for sure. So this is the same slide that we talked about before. Validity leads to underlies what underlies validity is reliability. What underlies reliability then dimensionality. So everything that we're going to talk about assumes that we know dimensionality, that we have a unidimensional measure, that the items measure one thing, and therefore that we can talk about reliability with which that one thing is measured. So back to this. Classical test theory, the logic that underlies summing items to be an indicator of the trait. So your total score, otherwise known as your test score or the item total, it's the sum across items or the mean. It honestly doesn't matter which it is. People tend to take the mean to address missing data, which creates a type of mean imputation in so doing, but it's still the same set of problems. You have this composite across items. And that composite is supposed to reflect, to some extent, your true score, and hopefully to a less extent, some kind of temporary measurement error. And so if you were to administer the same sets of items over and over again to a person, they might not have the same Y total. They should sometimes maybe be a little high or a little low, but the errors should cancel out. And so the expected value is the total, because the errors are supposed to wipe out of the equation. And so if you believe this, then you can have a framework with which to index reliability. And that boils down, in this case, to proportions of variability. Of the total Y-score variability, how much of that is due to actual real individual differences in the true score versus error variance? And so the ratio of the two then is true over total is thought to be reliability. Understanding how this actually turns into numbers requires us to remember a few basic things from statistics. So actually, I just taught this in my earlier class. Remember means and variances? Remember those? I should be seeing nods, right? You guys should remember means and variances. Yes. Just to remind you that you know what it is. But with a little bit of a notation switch, we're talking about the variance across subjects for a given item. So each item has its own version of a mean, its own version of a variance across subjects. We're going to talk a whole lot about covariance. So I wanted to remind you that yes, you've seen this before, although you may not have dealt with it very much. Covariance is the extent to which two observed variables go together. The extent to which if one variable tends, if a case is above the mean on one variable, to what extent are they likely to be above the mean on the other variable? Where if they're above the mean on both, that creates a positive covariance. If they're below the mean on both, it creates a positive covariance. If it's off, one positive and one negative, then that's a negative covariance. We don't typically report covariances because they're in a metric that isn't helpful. It's in the metric of the individual units of the variables. So I could have a covariance that works out to be like 156. Is that good? Like, is that a lot? I don't know. If it's positive, I know that cases that tend to be above the mean on one variable tend to be above the mean on the other, but I have no idea what 156 is. So what we're used to dealing with instead is the standardized version, which you know as correlation, and Pearson correlation, more particularly. In this case, there's lots of kinds of correlation that we'll talk about in this class. And that's a way of standardizing covariance. In the latent trait models that we're going to be working with first, CFA models, it's all about covariance. So we will stay in the original metric. So we'll end up with regression type solutions that are designed to predict the covariance between items. And if we standardize those solutions, like the same way that you can have standardized slopes in regression, those are supposed to predict the correlations instead of the covariances. So we'll have both of those, but the parameters of the models are phrased in terms of covariances for all of this stuff. So I just wanted to remind you that you've seen this before. Okay. So for categorical indicators, what do we do then? Well, if we have binary variables, we can still compute a mean, a variance, and a covariance. We might have ordinal or nominal though, in which case, if it's nominal, means and variances make no sense. So we're not going to talk about nominal for like 2 months. Okay, so nominals left the building for now. If you have a nominal outcome, we can analyze it, but just not until like November. We'll talk about that. We'll stay in the world of quantitative outcomes, binary or ordinal. For binary, when we talk about summary statistics of a binary variable, we can talk about the mean. That gets a special name. It's called the proportion, and it's the proportion of cases that have a 1 instead of a 0. You will sometimes see that proportion abbreviated as P. It's the same thing as the sample mean. It's just a relabeling. Q is sometimes used to indicate the proportion of zeros, which is 1 minus P. And the big deal about binary variables is that the mean and the variance are yoked together. So the normal distribution is really one of the few in which you can have a separately estimated mean and variance. They can each be whatever they want. In a lot of other distributions, including Bernoulli that underlies binary, the variance is determined by the mean. So you don't need to calculate the variance, you know what it is. So if you have a variable where 50% of the people got a 0 and 50% of the people got a 1, you know that the variance of that variable has to be 0.25. Has to be. So what that's going to mean for us is that when we get to the point where we're predicting binary outcomes as observed measures of the trait, they can't have an error variance. Because once we know what each person's predicted probability of a 1 is, we know the variability around that, and we know that it has to vary as a function of their predicted probability. So error variance is going to leave the building after we don't have variables that have separately estimated variances. For ordinal indicators, for something like this, a scale of 1 to 5 measuring agreement, you see this kind of thing all the time, and people won't hesitate to compute means and variances for this kind of scale, but it should give you pause. Or to use a technical term that I like, squishy. This should make you squishy. Squishy is my word for uncomfortable, because an ordinal variable is ordered, but it's not a number, right? I could say that strongly disagree is 1, disagree is 20, neutral is 300, and so forth, right? And that's equally valid to do because it still obeys numeric ordering. The distances between are the thing that's up for grabs. So this distinction is often ignored. You will see ordinal indicators treated as if they're really numbers, but they're not. And treating them as if they're really numbers gives you an optimistic view as to how reliable those indicators actually are. So we will see this when we contrast models, confirmatory factor models that pretend these sorts of indicators are actually numbers that are continuous versus models that understand that if I have a 1 to 5 scale, all of the predicted item responses have to be 1, 2, 3, 4, 5. They don't actually go on forever like a continuous quantitative variable would assume. The variance that you can have for an ordinal indicator is going to be limited by the number of categories. So the variance is separately estimated, but it's not completely separate. There is still some sort of yoking that goes together there. All right, you guys froze for a minute. Am I frozen or am I still here? I'm back. All right, are you guys still awake? You still with me? Okay, hanging in there. We're almost done, I promise. We're getting there. So ways that indicators are summarized, then these terms, like the mean of the indicators, that's going to get a special term now. So we get some new vocabulary coming in. All indicators in this class, in models for reflective indicators of latent traits, are going to have at least two properties. They're known as difficulty and discrimination. The models that we will look at differ in how those properties are operationalized and in what metric. So the terms are item difficulty and item discrimination to be consistent with the broader literature, like that's always what it's called. But you can think indicator, right? Just sticking with the idea that the observed variable that you have, that thing, has a difficulty and it has a discrimination. Item difficulty is location. It's where on the latent trait the item is located. So you can think of items that are easy versus difficult. Easy items are designed to measure people of lower abilities, whereas more difficult items are designed to measure people of higher abilities. So all items are not created equal, and that's a good thing. Indicators and items are the same thing in our class. Yes, they are. So I try to stick with indicator, but in this context, people never say indicator difficulty. That's not a thing. They always say item difficulty and item discrimination. So we want, in a measure, to have items that differ in difficulty. We want to have items that vary so that we can measure people who vary in the trait at a corresponding level. If you are dealing with a trait that is not academic, then you may think of difficulty as severity. Go back to that. So if you think about severity of symptoms, like how depressed do you have to be before you would agree with this statement? Or how low of, like if you have an attitude towards something, like how permissive would you have to be to agree to this statement? So severity is the way of thinking about difficulty, but it's still a location parameter. The other one is discrimination. And that's, in short, how good an item is. It's how related the item is to the trait. It's going to be some kind of slope in most of the models that we'll talk about. Items that have stronger discriminations are more related to the trait. They are more able to distinguish between people of different trait abilities. They are better items. There's a stronger signal there. So in classical test theory, the way that item difficulty is operationalized, because we're saying that the best estimate of the latent trait is just the total score. So the total score is the trait. Because we're saying that, the location of the item, its difficulty, is just the item's mean. So if I have a binary item, it's the proportion of people who got it right. If I have a quantitative item, it's the mean. Now, there's only one problem with this. In terms of the labeling, it's backwards. It is backwards. So if I have an item that 90% of my class got right. That item is of high difficulty, but it's actually easy. It's backwards. Eventually, we will get to a model where there's a minus sign in it that fixes this. But for now, it's backwards. So conceptually, flip it around in your head, but it's still, you can think of it as a location. Now, what's problematic about this particular definition of difficulty is that the items and the people are necessarily lumped together. So let's go back to that item. If I have an item that 90% of my class got right, because these are the kinds of item statistics that you get back. Like if you give an exam and they give you back your scores, you get these sorts of item statistics. Is that item easy or is my class smart? Meh? I don't know. They're yoked together. Likewise, is my class not so smart or is the item hard if only 10% of the people get it right? I don't know. So that's what I mean when I say that the items and the people are tied together. It's impossible to talk about the qualities of an item without also referring to the level of ability in your sample. They're yoked together. In the latent trait models where we're headed, difficulty is going to become an intercept of some kind, where it becomes the expected item response conditional on a given trait level. So that breaks the tie between the persons and the items. In classical test theory, even though items differ in difficulty, that's not often a characteristic that is used to select or remove items from a scale. It only matters if their level of difficulty is extreme enough to cause problems with discrimination. Because if I have an item say that only 2% of my people got right, that item is going to have a hard time correlating with anything, right? Because that item is almost a constant. So to the extent that extreme levels of difficulty impede correlation, then we have a problem with discrimination. So discrimination, under the assumption that the best estimate of your trait is your total score, is the correlation of that item with the total score. And because that's somewhat circular, because the item contributes to the total score, a lot of software will offer you instead what's known as an item remainder correlation or something along those lines, where what they do is compute the total without that item and then give you the correlation of each item with that modified total. That way you're not correlating an item partially with itself. And in this case, more is better. You would tend to look at these sorts of statistics and say that an item that has a stronger correlation is a better item and should be selected more than an item that has a lower correlation. In practice, this can't be right if the item has a nonlinear relationship with the trait, in which case the correlation is only going to be really applicable at the range, the location where the item is. So these correlations are overly optimistic if your items or your indicators have boundaries to them, which would enforce a nonlinear relationship to the trait. So we'll get to that later, but that just means that these are optimistic. What would happen if you had a negative discrimination? We talked about this a little bit last time. Can you have item discrimination that's negative? You could. Is that good? No, no, not good. Yeah, that means that as people who score higher on the item scored lower overall. That's not good. So if you see that something went wrong, something went very wrong. Maybe you forgot to reverse code it or something like that, but that's a bad item unilaterally. Otherwise, just more is better. Just keep in mind that when you're looking at the correlations, if you have a very low correlation, that could be because of range restriction, if it has an extreme level of difficulty, in which case you might want to keep that item because it's going to measure people of corresponding extreme trait weight. trait levels. So we'll talk more about that in the world of IRT, which people use to create short forms and whatnot, what to choose items. So the total score is the big thing that we're dealing with here. That's the indicator of the trait. So in order to use the total score, we want to know how reliable it is. How consistent is it of a measure of one thing? Because we've already assumed dimensionality. We want to know how consistently it measures that one thing. And the way that reliability is talked about theoretically is logically inconsistent with how it's actually operationalized. The way that we think of reliability is if I did this over and over and over again, would I get the same result, right? Like I said the other day, my Fitbit I think is reliable, right? I am pretty sure that the algorithms on it are consistently being applied. Now, whether it accurately is tracking my number of steps or my heart rate is another question, but I do believe it's consistent. Every day my Fitbit behaves consistently, I think it's reliable. But when you deal with samples of people, it is rarely the case that you give a measure multiple times, right? You give it one time, and you want to still be able to compute some kind of reliability. So rather than thinking about consistency as a property of a person, it's operationalized as a between subject characteristic. How much of the variability in my total score is due to real individual differences in the true score versus error? So we're taking a leap from an intra-individual kind of concept, and we're talking about it in an inter-individual sort of way. There has been an increased interest in recent publications about reliability of within-person measurements, recognizing this problem, that the extent to which if you did give a measure multiple times, so what's known as intensive longitudinal data or EMA data, ecological momentary assessment data, there's a lot of that nowadays because you can ping someone on their phone and make them answer questions. And if you do that several times a day for several days, you get a shit ton of data per person. And if you get enough people to do that, then you have a lot of people, then potentially you can think about reliability in two different kinds of ways. Like to what extent, does one person give the same score across time, right? Are they an internally consistent kind of person or do they fluctuate a lot? And then across people, to what extent is the variability that's being shown due to true differences between people versus error? And so those are actually two different things that you can operationalize in two different ways if you have the data. But most of the time when people are talking about reliability, it becomes a between subjects idea because each person only has one data point, or two at the most in this case. So here's the logic by which if you get two scores per person and you correlate them, that number all of a sudden becomes the proportion of total variance that's true. So it's a leap of faith. So if I have two scores, y1 and y2, and they vary across subjects, in theory, if each of these scores is measuring the same latent trait, then it's the same trait for each person. So t is the same, but then error is different. Error is subject and item specific. If we're willing to assume that these two errors have equal variance, and we're willing to assume that these two outcomes have equal variance, and we're willing to assume that it's the same trait both times, and that error and trait are uncorrelated, then we can start with just a correlation between these two variables, break it down into its component parts. So here's the formula for Pearson correlation. It's the covariance between y1 and y2 divided by the two standard deviations. Y1 is supposed to be a combination of true score plus that item's error, and Y2 is supposed to be a combination of the same true score plus a different item's error. And do you remember foiling? Remember that from like 8th grade algebra? FOIL? What is it? First, outer, inner, last? Yes, thank you, Kayla. Like, I know what FOIL stands for. If you FOIL that combination, you get this. So we have the covariance of the true scores, we have the covariance of a true score with the first error, that's supposed to be 0. The same true score with the other error, that's supposed to be 0. And amongst the two errors, that's supposed to be 0. So you're left with just the covariance between the two true scores, which is its variance, which is this thing over here. So if you believe all of these untested assumptions, you can take the correlation between two scores, two total scores, and call that the proportion of true score variance. Ta-da! So then a lot of reliability falls out of that basic premise that you only need two scores and their correlation tells you something. So there's two scores. You can get the same test multiple times, known as test-retest reliability. You can have alternate forms of the same test, and you can only have one score and just look at the correlations among the items. So those are the different ways that reliability is going to be operationalized. We'll talk very briefly about the first two and then focus on alpha. So how many of you had to take the GRE to be here? Let me ask you this, changing gears. Most of you? I just learned this morning that a bunch of academic programs on campus have stopped requiring it or using it altogether. And I volunteered that that is actually a really good thing because as it turns out, the GRE is not really that reliable. When you got your scores, did you get a standard error that went with them? No. No. So I have for you later on a slide here that's giving you what the ETS company who sells this product thinks their reliability is and what the standard errors of measurement are. And it comes out of some of the same stuff, particularly with the subject test. So each of the areas that you might go to graduate school in, some of them have a particular test you have to take, like in psychology. I know I took that one. They use alpha to indicate the reliability for that. And it's actually very high reliability because they have lots of items. So that's what we'll get a chance to explore next week is how to hide behind alpha. That's the big one. All right, so summarizing today, EFA is unnecessary, don't bother. Classical test theory is adding shit up, but it causes problems when you try to extrapolate to new samples, but it's a place to start. And it is actually going to represent a whole bunch of untested assumptions that I will show you the way to test in latent trait models starting next week. How's that sound? All right, if you haven't already done so and you know how to get into the virtual desktop, please see if you have access to M+. I'm going to put together a handout that shows you how to get to the virtual desktop for those of you who haven't had the chance to do that before. And if you run into any problems, let me know. Otherwise, if you haven't done homework 0, please do that by next week. And since it's not garbage day, that means it's Thursday, which means I say have a good weekend. Please take care of yourselves and let me know if you need anything. Okay? Okay. Then peace out, guys.